what they try to do, as I mentioned earlier on, the cute thing about GANs is to try to learn generative models while having two dually discriminative networks. Two feed-forward networks that we know how to train, but between them, they learn the generative model. That's why they sort of pay popular. But they are actually learning generative. Okay? But keep that in mind. So if I were to learn the Bayes network that I showed you in the previous slide, would I be learning a generative or a discriminative model for a Perl scenario?
Generative.
How many people think I would have learned a generative model if I learned that distribution? How many think I would have learned a discriminative model? Okay. It is a generative model because essentially I can give all the active samples. Basically, I can give you, given any variables, I can give you the other variable. It's a full generative model. It reproduces the data. The thing about generative models is, so here is the other thing I'm thinking about true-false questions. So my son was telling me that his teacher figured this out, that for their second midterm, they were asked to write a whole bunch of questions. Not the answers, the questions. That, thankfully, this teacher will use the next semester for the students. You think writing answers is the hard part, right? No. Writing questions that have answers is much harder. Okay, so he was asking his students to write the questions. Can you generate questions for AI? If you generate questions for AI, then you have a generative model. If all you know, so if I instead of just giving true, false, and then you mark true or false, if I say, okay, false, give me a false statement. True, give me a true statement that is relevant to AI. The more you can say about that, the more you understand about AI. Okay, for example, tell me something non-trivially false about exploration versus exploitation. To actually come up with the question, you need to have a generative understanding of AI, not just a discriminative understanding of how to do well on a particular question. Okay? So statistical learning has generative models, it also has discriminative models. Oftentimes you wouldn't have heard of the discriminative models. In fact, we will talk about something called naive-Bayes classifiers. Naive-Bayes classifiers are essentially learning generative Bayesian networks of a particular kind, where they assume of this following type. Naive-Bayes classifier assumes that the class Y causes all the X's. That's the network. That's the naive-Bayes network. So if I can learn this network and its computational probabilities, I can learn this network. It's a special case. We will mention it, but it's just a special case for us. Naive-Bayes classifier happens to be a generative model. Okay. For the classification tasks, in the statistical scenarios, logistic regression turns out to be a discriminative model. It directly captures the Y given X, not capture the joint distribution. For the sequence learning tasks, you may have heard of two names. I won't actually go into the details here, but it's useful to know. HMMs, hidden Markov models, versus CRFs, conditional random fields. One of them is generative, the other is discriminative. HMMs are generative, CRFs are discriminative. And it's not surprising, now that you know the distinction between generative and discriminative, you know that more people wound up using CRFs because there are a lot less information to learn from the data, so you can get by with less amount of data. Do you see what I'm saying? Because understanding all of AI so that you can also set the final exam requires a much higher amount of understanding than understanding the pattern on the true-false questions that I'm going to say. For the second one, maybe you just need a couple of examples. For the first one, you probably need, paying humongous amount of attention all through the semester and class. So learning generative models are actually costly. And so you have to make some kinds of assumptions to make the generative models learnable. But if you do learn the generative models, then they're going to give you a lot more leverage. Yes?
You used the term as you were talking earlier, fully generative model. So I guess.
I think it's just generative. There is not the word fully doesn't mean much.
Okay.
Generative essentially means you can take any piece of the data, I'll give you the rest of the data. Discriminative means that certain parts of the data are called the class variables. And I'll only tell you class variables given the input variables, never the other way around. Okay? Again, this is the same thing. So if I were to make a spam mail classifier, a spam mail classifier might be able to very correctly predict whether mail is spam or not without knowing what a mail is. If it's a discriminative classifier, it will just tell you whether it is a spam or not spam. And if you ask, can you show me what you think is a mail? Can you produce a spam mail? It has no idea. Now, why is this interesting? It turns out that the generative versus discriminative thing has been an ongoing discussion, ongoing argument in machine learning community. And this basically summarizes what I've been saying. Okay? So by effect, the joint distribution is what generative model tries to compute and learn, and then discriminative model only learns the conditional distribution. And so in some sense it learns less information because, as you can see, if you only learn py given x, if you want pxy, which is the total joint distribution, this is not enough. Sorry, this is not enough. You want to multiply it by p of x. That's just chain rule. That tells you what you are losing in discriminative models is you are not modeling the dependencies between the variables of the data, input variables of the data. Do you see what I'm saying? You're only actually looking at how do the input variables change the output variable, the class variable. But you are not modeling the dependencies between x and z. Which is why, even if you are very good at saying this is spam mail, if I ask you to write a mail, you will write gobbledygook. You have no idea what a mail looks like. And if I know that you have no idea what a mail looks like, then I can basically be adversarial and I can generate spam mails that look non-spam to you because you don't actually have an understanding of what a mail is. How many of you are thinking of ostriches? From the very beginning of the semester. Remember, neural networks are humongously large discriminative models. And we said, basically, you can make them see ostriches everywhere, or anything everywhere. Because you have no actual idea as to what they are looking in the picture. Because they can't actually generate the picture, they can only see the picture and give a label. So, one way of making sure that the adversarial attacks are reduced is to go with generative models. Show me what you think is a cat. Show me what you think is an ostrich. The reason we couldn't make sense whatsoever of those ostrich examples is because you can't see for the life of you where is the ostrich in this South Indian temple, the school bus. But the network thinks, yes, I see an ostrich. So then I want to ask you, show me, when you say cat, show me the picture of the cat in your head. And then you say, no, I'm sorry, I'm a discriminative model. I'm not a generative model. I don't know what cats are. I can tell you, given the input, I'll say cat. You see what I'm saying? So in fact, even though generative versus discriminative models has been an ongoing discussion in machine learning for a long time, now it's actually back in, with a lot of interest currently in the community, because essentially very large discriminative models cannot explain what the heck they're doing because they can't actually produce the data that they are classifying. So in fact, there is a popular quote attributed to Feynman, who is another of the guys who was into aphorisms after doing physics for a while. And he said, you only ever understand something if you can create it yourself. Of course, he was trying to understand the universe. So you can imagine that he has certain rather, he thinks very highly of himself. So he was hoping that he will create the universe. Okay. But he said, you only understand something if you can create it. That's kind of true. In some sense, when they said in that funny thing that I hear, when I hear something I understand, I teach something I understand more, I program something I understand the most, etc. All of that is essentially saying that you are going towards generative models. You can do very well in the true-false question and still not teach AI to your nephew or niece. Because all you learned is, 90% of the time false is the answer. They'll say, you're kind of brain damage. This doesn't seem to have anything to do with it. Okay, so you need to understand much of what happens is going towards generative models. And in fact, in neural networks right now, there's a lot more interest as we speak. In fact, yesterday there were like 5 or 6 papers on arXiv trying to say how to get out of adversarial examples, the sensitivity to adversarial examples, by basically going for generative models. Okay? There was a yes.
Is this how deep dream works?
What?
Is this how deep dream works?
Deep dream?
Yeah.
No, deep dream is actually, it's again, the part of deep dream is, if you take the entire deep dream, then you are taking a discriminative model and you are playing with the discriminative model until the picture that you are showing it, it will keep saying it's a cat, or it's an ostrich, or it sees whatever. Okay? So it's the model, the network itself is discriminating, but there is this extra process that you are doing on top of it that's making it a little more generative. That's a good point. And you also notice that I mentioned this in one of the slides after the discussion in the class, that the distinction between deep dream and adversarial examples is very thin. Okay, adversarial examples, you change the image until the point where the network itself with high certainty thinks there is an ostrich in it. But you still don't see an ostrich. So why isn't showing Indian temple and say ostrich, why isn't that a good deep dream example? I know that my network says it's an ostrich, but you guys are not impressed because you want to see ostriches. If on the other hand I kept changing the input image furthermore, while it still is ostrich, then what you will start seeing eventually is you will start seeing sort of hallucinations of ostriches on the picture. At which point you say, yeah, I see your dream, your hallucination. The worst kind of hallucinations are the ones where I don't even see your hallucination, and they become adversarial. Okay? Yes?
So the generation in case is not actually fully generated.
It's generative if you put the whole picture and you come outside of the picture, it's generative. It is generative. Okay, so that's the thing that you want to understand, and basically again, even though this is a very well-known idea in machine learning for the longest time, it's become a lot more important again now because there are these really large discriminative networks who are finding crazy patterns about the true-false questions without understanding anything about AI. Do you see what I'm saying? So if you ask them to justify, your brain just blows. You can say, my God, you're getting 100% in my course and this is what you think is the justification for this answer? You should fail. That's what you will say to the neural network. Okay. Now, much less deeper stuff. Let's try to get a sense of how do people do basically learning in statistical sense before going on to Bayesian. The simplest idea essentially is you consider a competing hypotheses for explaining the data, and you pick the hypothesis that basically gives higher likelihood to the data. That's what is called maximizing the likelihood of the data. Okay, this is what you do in statistical learning. And to get that into your heads, consider this simple example. I have, you're about to toss a coin. I'm slightly worried that maybe you got a biased coin. I'm not completely trusting of you. I think you may have a biased coin. So in particular, to make my life simple, I think that really you have either this coin which comes up heads only 1% of the time, which means comes up tails 90% of the time. So it's a highly biased coin. Or this fair coin, which comes up heads 50% of the time and tails 50% of the time. I'm trying to learn which one do you really have. Right? That's what I'm trying to learn. Okay, so then I ask you to start asking the coin that you have. So I get the data. And the data basically is this. By the way, first of all, how many of you see this is a Bayes network? Here. Do you see this as a Bayes network? It's a Bayes network. It's a Bayes network with just one node. Everything is a Bayes network. This is a Bayes network with one node. And so I'm trying to, I think the Bayes network for your coin is either this or this. Okay, I'm trying to figure out which one it is. So I'm trying to learn. Okay, so I found this. Okay, so then what do you think? What do your intuition say as to which one is the coin that you currently have? What? This is the data. You guys have no intuitions? Yeah?
I would guess the blue one because it says it's a random coin and the probability of you having like a fair coin is higher than the probability of you having a random coin and there are
Okay, so you're overthinking it. Right? So imagine the following thing. So you are the kind of person who keeps seeing that tigers are kind of trying to bite you 18,000 times and you say, I think it's just random. Sometimes tigers bite, sometimes they don't bite. I'm particularly unlucky, so they're just biting me most of the time. So I will be fair to the tigers. I'll give the benefit of doubt. Good for you, because if people like you exist, there will be much less racism and bias in the world. But typically those people don't exist because they got eaten by the tigers. Right. Okay, so my question is, are there any non-racist, are there any racist and sexist people in this class? Closet racist and sexist people. Who basically, that's what we are all basically. Again, this is the point that you evolved to fight or flight. Okay, so you get a few amounts of data and you have to learn. And when you learn, you don't necessarily think about the feelings of the poor tiger. You run the heck out of, away from the tiger, and tiger feels offended, saying, I was a nice tiger. Really offended. You don't think about it. Okay? So anyway, so this one is saying take most of the time. So clearly, you would think it's the unfair coin. Because now you can actually quantify this. What is the likelihood of this data being generated by this green guy? Okay. So this, to get this head with this coin, I would have a 0.1 probability times 0.9 times 0.9 times 0.1 times 0.9 times 0.1 times 0.9 times 0.9 times 0.9 times 0.9 9. These are all multiplications. Multiply this whole thing in your calculator and you get a number. That's the likelihood of this data being generated if this was the hypothesis. If this was the hypothesis, which actually is a true hypothesis, the likelihood would be 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, etc. You see what I'm saying? And to the extent one likelihood is higher than the other likelihood, you'll say that is the Bayesian hypothesis. Right? That's what you will do. Okay. So in this case, in general, most of these likelihood-based approaches will say, well, obviously this must be, this data could not have been produced, is more likely to have been produced by a biased coin than by an unbiased coin. Right? That's basically maximum likelihood estimation. The only difference in really doing this is here I just compared the two hypotheses, P h equal to 0.1 and 0.5. Really, the hypothesis that I have to look for probability of h equal to a real number between 0 and 1. Every one of those real numbers is a different hypothesis. That is the probability of cutting heads. It can be 0.1, 0.10005, whatever, pi by 7 or whatever. Also, all of these will wind up being probabilities. And you have to consider which of them maximizes the likelihood. This is where calculus comes to the rescue. You will essentially set up this expression as a symbolic expression in terms of the theta. Imagine this is theta. Imagine this is, instead of this, it's considered as theta. Then what we're doing is theta times 1 minus theta times theta times sorry, this is 1 minus theta times theta times 1 minus theta. Do people see what I'm doing? And this is a huge big multiplication. And I'm trying to say, for what value of theta will this multiplication be? A maximum. One other thing. In most probabilistic reasoning cases, you assume data is independent and identically distributed. You keep seeing this thing, IID. IID is independent and identically distributed. Each data point is independent of other data point given the hypothesis, because the hypothesis is producing all the data points. And each of them are identically distributed. The same hypothesis is the distribution for all of them. In that case, you will always get likelihood will be a big product. Likelihood will be a big product. And you need to essentially maximize it. There are two issues. First of all, likelihood of a big product of numbers that are all less than 1. And if you have a million data points, if you multiply a million numbers that are less than 1, what do you think the answer will be? Underflow 0. 0 is forever. Whether it's because of your computational limitations of fixed point, precision of your arithmetic or not, 0 is forever. Secondly, actually, you have to use calculus, right? You have to use calculus on this huge product. You have to maximize a big product involving theta. That can be painful because you will somehow have to, either you have to use a humongous version of product rule of differentiation, because remember, you have to differentiate it equal to 0. That's how you will get the maximum. Remember that, it's the same thing. Either you set the differential equal to 0, or you can do the other thing, which is, imagine you want to maximize this multiplication. Suppose I take the log of this huge expression, logarithm of the huge expression. Then what happens? Logarithm of products is sum of logarithms. So if you just happen to stay awake up until the teacher came to the differential of log in your calculus class, then suddenly you can do log likelihood. If you maximize the log likelihood, it would be maximum exactly at the same theta value where the product likelihood become maximum. You people see that? Why not sign likelihood? Of course, other than the fact that sign is a crazy function, it's also sign is not monotonic. Log is a monotonic function. So if you take a log of this big expression, that logarithm would be maximized exactly at the same place where the product is maximized. This is why you do log likelihoods. You'll see this today's class. And log likelihoods makes things very simple in many cases. And in fact, just as, so for statistical learning people, they just hate it if there is ever a sum of probabilities. Why? If you have sum of probabilities and you take a log of it, nothing magical happens. You see what I'm saying? If you have sum of probabilities and you take log, nothing magical happens. And so in fact, those problems become much harder to maximize their minimums. In fact, for the EM case, in the expectation maximization case, that's exactly what happens. Because you will wind up not giving the values of some of the variables, which means you have to marginalize over them. That means you have to sum probability. Log of the sum of the probabilities, nobody likes that. Okay? So keep that and stuff in mind. Any questions on this? Yes?
I was stretching, I'm sorry.
Oh, good. Now for some candy. Okay, so this is what we will do mostly. This is MLE. And in fact, if I just tell you this, then you're done, you'll get your Google jobs. I never was interested in getting the Google jobs. I was interested in making sure that you keep the interviewer interested in your conversation. Not just give the answers they want, but essentially how do you think. Okay? So I want you to understand that maximum likelihood that we are doing is the poor man's version of what is the right thing. It is Bayesian learning. So we'll come back to this except after 3-4 slides. Okay? That's where we are talking about Bayesian learning, and in the Bayesian learning, we don't pick an hypothesis at all. We keep all the hypotheses around. This is what I was saying in the beginning. But I will illustrate it. If you have continuous hypothesis, to illustrate that, I need to talk about integrals. Right? So I will do discrete hypothesis. So I'll give you this example where, this is directly from Russell's textbook. And so Russell apparently just hates lime candy and he likes the cherry candy. And so he has figured out that there is a bag of candy. It's in a brown paper bag. It's like, I guess just like other people get beer in the brown paper bags, he gets candy in the brown paper bags. Okay, and he's taking candies one after other. Okay, now assume that he's doing it with replacement. I mean, he looks at the candy and puts it down. Maybe looks at it, licks it and puts it down. Okay, but he knows upfront that the candy, there are only 5 types of candy packets. Type 1 is all cherry. Type 2 is 75% cherry, 25% lime. Type 3 is 50% cherry, 50% lime. Type 4 is 75% lime, 25% cherry. Type 5 is all lime. Actually, I'm sorry, I'll keep this in mind, but I want to complete one other part which I forgot to mention, given all the thing about tiger. I'll just do that. So you did this about logarithmic likelihood, right? Now, forget about this data. I want to give a different data for the same problem. I just happen to get this. So I just tossed the coin twice. HTT. Now, what do you say? Now what do you think is the more likely hypothesis? Are you going to jump to, my God, you had an unfair coin, it came twice, tails? Or are you going to say, statistically it's quite likely that you can get 2 tails? So clearly this girl now will say, yes, I finally win. There are good tigers in the world. Okay? Because you can't just assume that tigers eat because they ate about 3 people. You have to wait until they eat a lot more people before you generalize. You understand what I'm saying? So she doesn't want to jump to conclusions. Right? Now, so here in this case, you want to say that even though this guy's data likelihood is higher given that hypothesis than this hypothesis, you don't want to believe that that is the cap point. Why? So what? Why?
So have to see the prior.
Yes, the difference between that girl and the rest of you, and you have different priors. Okay, some people think the world is made up of nice people, and some people think the world is out to get me. They have priors. The reason you agree with this idea that here most of you probably think I don't want to rule out it being a fair coin. The reason you don't want to rule it out is not because the data is small, but because you did have a prior. All of you had a prior. Your prior said most people tend to have fair coins. It actually requires work to go out and get an unfair coin. So if randomly somebody picks up a coin, it's probably fair. So the prior probability of a coin being fair is much higher than it being unfair. I will start with that prior, and the data can push me to disbelieve you. This is what I'm doing when I said the prior probability. When I say, for example, I'll give you the benefit of doubt and assume you are all honest, I'm assuming that the prior probability of you being honest is higher. I assume so. But you can convince me otherwise. If the entire class cheats, then I'll say, okay, sorry, my prior has now become posterior. Posterior, given the data I have seen, is you guys are all cheaters. Data can change the prior. It can override the prior. So in some sense, you already, even normal statisticians who don't believe in hypothesis prior, actually believe in hypothesis prior. They think certain things are more likely than others without having seen the data. Do you see this? That's where you realize that actually MLE must be the special case of a much more general idea. And the general idea is the base general. Okay. So anyway, so you go back to this. So what I'm going to do now is and then I have this, and then one of these bags has been given to me, and I'm picking coins, picking candies, and I'm getting an unending array of cherry candies. I'm sorry, lime candies. Now I want to ask two questions to myself. Question one: what kind of a bag is it that I'm picking the candies? Remember, I have a brown bag. I don't know which one of them. It's one of these, I don't know which one it is. What kind of a bag am I picking the candies